Hello, what is up? And welcome to Radioactivity Academy. This is Mike Warrior, and in this video, we're going to look at question A21. This is Science Paper 1 Physics. That is GC. Yeah, so welcome to this video. So we'll be looking at specifically something to do with radioactivity. Okay, so for those that are watching me for the first time, please make sure that you do subscribe. And there's a video that is already up on my YouTube channel, which is Radioactivity Academy. So make sure you check it out so that this question can actually make sense for you. Okay, so now the question says, radioactive isotope has a half-life of 6,000 years. How much time passes before the rate of emission from a sample of this isotope falls to 1 out of 16 of the original value? Okay, so when it comes to half-life, the relationship between the activity and also the mass of that radioactive isotope. So all you have to do is draw a simple box table, okay? And then you do that, and then on your left you put the time, and then on your right you put the activity, okay? So what happens is that as the time keeps on increasing, the activity should be able to reduce by that half-life. So if you start, for example, number 1, so the idea is that the half-life is in years. So I'm going to say 6 years, okay? So this is in years. Okay, so 6,000, okay. So what will happen to the activity is that half of this, of the activity, let's say the activity, you can have the mass, which this x can be regarded as the mass, okay, that can be given in grams. But since we don't have anything to do with the mass, so this is what is reducing or disintegrating, okay, like breaking down into some other simpler masses, okay. So what you're going to have is 1 over 2 times the original value, which is the x, which can be in as a mass. So this is just going to be just 1 over that. It should just be 1 over 2x. And then the second one, so the idea is that when you reach at this 1 over 16, we have to actually stop, okay. So what will happen is that the time will keep on increasing. So in the next activity, you're going to double this one to be 12,000. And on this part on the activity, you have now two half-lives, okay, multiplied by the original mass. And then just keep on doing that. And this now will give you 1 over 2 times 1 over 2, just 1 over 4. Okay, 1 over 4. And then 3. Then we keep on adding to get the third number. You say this times the previous one. This 12,000 plus the previous one, which is going to be 18,000. And on this one, you're going to have 3 half-lives, okay? So this is going to be 1 over 2 over 1 over 2, okay, which is just equal to 1 over 8. Okay, so just write the direct number 1 over 8. Okay, multiplied by the original mass, just going to have 1 over 8x. Now remember, this x is representing the original value. Okay, so now because we don't know what x is, we just kind of pretend as if we know it, and then we just tend to multiply. Okay, so now the last one is going to be, so this 18,000 plus the initial starting value, I mean this will be just the 24. So this will just be 24,000. So you have how many of lives? 4. So you're going to have 1 over 2 multiplied by 1 over 2 multiplied by 1 over 2 multiplied by 1 over 2, which is just the 1 over 16. So the moment you reach at this number, which is the number that they have actually hinted there, is that you need to stop. So 1 out of 16 multiplied by x, which is the original value, and this will just be 1 over 16 of that original value. Okay, so from there now, once you reach at this point, you need to stop. Now you ask yourself, what is the time when the activity or the isotope activity falls to this mass? So 24,000, okay, so 24,000 years, actually how much 1 out of 16 will be reduced of the original mass. So they're saying that how much time. So how much time, meaning it is going to be just 24,000. So when you check on your answers, the answer is C. Okay, so thank you so much for watching. Please make sure that you subscribe, you like, and also you share this video to your families that are in need of this kind of information, and even just to your friends. Make sure that you just share it, okay? So thank you so much. I'll see you in the next video. So now the question reads, uranium-238-92 decays to form a nucleus of thorium by emission of an alpha particle. Thorium has the symbol 234-90Th. What is the meaning of a nucleon? What is the meaning of a nucleon number? Okay, so now the mean on A, the answer is simple. When you talk about the nucleon number, this just means that it is a number that represents the total number of okay, so the nucleon number means that it is a number that represents the total number of protons and neutrons in the nucleus of an atom. Okay, so as simple as that. And then now B, write a decay equation to show how uranium-238-92 decays to thorium-234-90Th after emitting an alpha particle. Okay, so now we are writing. So we are writing the equation. So the thing is that you have is uranium 238 and 92, and then you write an arrow, and then from this arrow, since they are saying it is emitting an alpha particle, so an alpha particle is just an helium atom. So you do that, helium atom, and then plus now what you do is that if this is actually emitting an alpha particle, then the mass number of this radioactive isotope must be reduced by 4. So we're saying 238 minus 4, you're going to get 234, and then 92 minus 2, you're going to get 90, and this is going to be TH. Okay, so this is an equation that you just needed to write. Okay, and then now we move on to the last question. So these questions are on C. Now, thorium-234-90Th decays to an isotope of protactinium, Pa by beta decay. Write the decay equation to show this process. So again, this is a beta decay. Okay. So now what's happening is that it is thorium. So you get thorium-234. Okay, so this is C. 234 TH and 90. And then you put an arrow to show that it is producing something. So it goes by the beta decay. So a beta is just an electron in nature. So you write the symbol of an electron, and it is negatively charged, then doesn't have the mass, then plus. So when you're dealing with a beta decay or an electron, you add the numbers. So 234 plus 0, just get 234. Okay, and then 90 plus 1 is just 91, and then you have this substance or isotope formed as in protactinium. So this is just the decay equation that he wanted us to show. So make sure that you understand what is going on, what is the emission, what kind of radiation or particle is being emitted. So this is a beta, and this is how we show the beta decay. So thank you so much for watching. Please make sure that you do subscribe, like, and also comment. If you need some tuitions, online lessons, just comment in the comment section below. Thank you so much for watching. I'll see you in the next video. Hi guys, what is up? This is Professor Wadia, and welcome to Radical Academy. This is question C3, or rather section C, and specifically on question C3. This is Science Physics Paper 1 and GC 2021. Okay, so we are looking at this radioactivity question. So for those that have not subscribed to my channel, there's a plenty of videos that can help you understand the whole topic of radioactivity. So make sure you subscribe to this channel for more information so that you don't miss out. So each time we post an update, you are going to receive a notification that we have posted a new video. Okay, so now let us dive into this question. So the question says the atomic number of americium-241 is 95. Americium-241 decays by losing an alpha particle. Question A, Roman numeral 1. Explain why smoke detectors containing americium-241 are not harmful to people. So this is A1. Okay. So the answer is simple. So we are going to say that the smoke detector is contained because the alpha. Okay, so let's say because it contains the alpha radiation, or simply produces produces alpha particle. Okay, alpha particle is that have okay. So it's because it contains the alpha radiation or produces alpha particles that have the lowest penetration power. So as simple as that. Okay, so now we have this question 2, Roman numeral 2. Copy and complete the equation showing this decay by giving the values for x and y. So you can see that this is an alpha particle. So americium 241, so Am 95 is equal to that, and then 4 2H. Okay, so plus X, and then Y, and then the substance is Np plus some energy. Okay, so on this one, what you do is you have to look at this the alpha. So for us to find this one, you have to say 241 minus 4. So we're going to say x is equal to 241 minus 4. Okay, and our x is just going to be 237, I think. Okay, so it's 237, and then also the y is going to be y, so it's y equal to 95 minus 2, and the y is just 93. Okay, so now you have to understand that whenever you're dealing with an alpha particle or decay, is that both the mass number for this isotope and the proton number will reduce respectively by 4 and 2. Okay, so these are the values of x and y. So therefore, the completed equation is just going to be 241, then 95, that so you're going to have 237, and this is NP, and we have 93 there. Okay, plus some sort of energy. Okay, so this is what you need to understand on this one. Okay, so you have completed everything. So what to follow now is the table. Okay, so when you look at the table, figure C 3.1 shows how the activity of a sample of americium 241 changes over a long period of time. So we have the time and the activity, which is counts per minute, and then the questions that follows use these numbers to draw a graph of activity against time for americium 241, and use your graph to find the half-life of americium 241. Okay, and californium 241 is also radioactive and decays by losing an alpha particle. There's a half-life of 4 minutes. So just why it would be unstable and suitable for use in a smoke detector. So now let us, on this one, you need the graph paper. Okay, so you need the graph paper, and before that, what you need to understand that these values that they have given you, okay, when they say draw a graph of activity, so this activity, what they mean is that it's going to be located on the y-axis, and then the time is going to be located on the x-axis. So these are the key concepts, okay? And then the other key concept is that we need to find the scale that you're going to use. Okay, so whenever you are looking at the graphical work, you have to ensure that you use a pencil. But for the sake of presentation, I'll use a pen for clear and visibility. Okay, so since this is the time is the x-axis, so you'll be plotting like 0,64, okay, just like 0,64, 500, that, 500, 30, then also 1000, 14, and 1500, 6, and 2000, 2. Okay, so this is how you'll be plotting. So these values represent x, and then these the y. Now the other thing is that we're supposed to come up with a scale. So when you look at the numbers, we are going to use a scale of on the y-axis, okay? On the y-axis, our scale is going to be, when you look at 2, 6, 14, 5, so we're going to say, let's 2 centimeter is going to represent 5 units, okay? And on the x-axis, or on the x-axis, you're going to have 2 centimeter to represent 2 centimeter to represent 500. So 2 centimeter represent 500 units. So this will kind of be like draw something like this. Okay, so this is how it's going to look like. So in the x-axis time, so this is x and this is y. And we know that the intersection is 0. Since there are no negative values, so you don't have to include the negative values. So what will happen is that you have every after 2 centimeter, you'll be putting 500, 1000, 1500, then also 2000. Okay, and then also on this one you have 5, 10, 15, 20, until you reach at 65, because you are using the units of countings like every after 2 centimeters is 555. But we know that the highest number on the counts per minute is 64. So the key thing is to follow the scale, okay? Follow the scale. So once you just kind of plot it, you have 0,64. So 64 maybe will be somewhere there. And then 500, 30. So like 30 is, let's say, for the sake of just argument, somewhere there. And then 1000, 14 is maybe somewhere there. And then maybe 1500, is somewhere there. Then 2000, 2 is just somewhere there. So your graph should come out like this, okay? So your graph should come out like this. Okay, so this is how it's going to look like. Okay, so but I have to put it on a graph paper. So now that we know what's happening, guys, okay, so I'm gonna draw my graph. So all the way from down here, so you can just kind of start from here. So the y-axis is a bit longer, so I need to extend maybe somewhere there. Let's see. Okay, so I have to put the numbers. This is 0, so this is 500, 1000, 1500. This is 2000. Okay, so there you can just close. And the units in the x-axis is time, and it is in years. Okay, and then on the y-axis is 5. Okay, 10. Also this is 15, 20, 25, 30, then 35, 40, then 45, then 50. So I need to extend a bit there. So this is going to be 55, 60, then the last one on top, this is going to be 65. Okay, and then you write along here in the x-axis. Okay, so I mean in the y-axis, so you say activity. So activity, then it's in counts per minute. Okay, so count per minute. Okay, so now our scale. So this is a graph of activity. So activity, let's just say against time. And then our scale, you can just indicate the scale is x-axis. So the x-axis is 2 centimeter to represent 5 units, and also the y-axis is 2 centimeter represent 500 units. So now from there, now the most important thing is also to know how the scale is happening in between the smaller boxes. Okay, so from 0 to 500, what is the counting in between? So it is 0 every 2 boxes. Okay, it is 1. So 0. Now because it is 100, so we're going to say 0, 100, 200, 300, 400, 500. So that is the counting. So 2 small boxes, that is 100, 100, 200, 300, just like that. And then on the y, 0 from 0 to 5. So what's the counting? So it's 0, 2 boxes, 1. So 0, 1, okay, 1, 2. So it's 2, 3, 4, 5. Okay, so that's how we are counting. So now let's plot the numbers now. Okay, so these are the numbers. So 0, 0,64. So 0,64. So this is 0. Then you go where there's 64 in the y-axis. So this is 60, 61. Okay, 62, 60. This is 60, 61, 62, 63, 64. Okay, so this is where 64 is. So this is where you put, okay. And then now we have 500,30. So in the x-axis it is 500,30, and this is just here, and you go up, and then you see that there is 30 there. So this is where they are more like intersecting, so you put that. Okay, and then just to go direct now, 1000,14. So this is 15, and then 14 is there, and then 1500,6. So you have what you are following. This is a table. So 1500,6. So 1500,6. This is 5. Okay, this is 5. Then 6. And then now the last one is 2000,2. So 2000,2. So this is 0, 1, 2. Okay, so this is our 2. And now you can simply join your graph. You have to be very careful when joining the graph. Okay, so just smoothly. Okay. Okay, so something like that. And okay, so okay. Then also all the way from this side. Okay. So this is how our graph looks like. Very slanted, trying to go to the right, and trying to reach the x-axis, but not meeting, but just reaching, or actually facing the x-axis. Okay, and then curving a bit. So that is how it looks like. Okay, so make sure that you pay extra attention to that. Okay, so this one is done. So the other question is use your graph to find the half-life of this one. So when you're finding the half-life, all you have to do is the half-life is just 1 out of 2 multiplied by the highest number of the activity, which is 64. So this is give you 64, and this is the same as saying over 1. This is 1 times 64 is 64, and 2 times 1 is 2. So 2 into 64, this is 32. So this is 32 counts per minute. Okay. So now what you do is you get your graph. So the counts are on this side. The counts are on this side on the y-axis. So you have to locate where there is 32, and you get your ruler to do that. So this is 30, 31, 31, okay, 32 there. So you get your ruler, and then you put that, and then you say, just kind of a dot, you draw the dots, thereby meeting the curve. Okay, so the moment you meet the curve, now you stop, and then you drop down, because the half-life is a time. Okay, and then once you drop down, then you also do the same. Okay, so you continue doing the same until you reach the x-axis, because the half-life is a time. Okay, so you continue doing that until you reach where there is a value. Okay, so until you reach where there is a value along the x-axis. Okay, along the x-axis. So now you have to read off where this line has actually, ended on the x-axis. And what line is that? This line is, what value is that? So 0, 100, 200, 300, 400. Now 500 is this one. So the line is in between 400 and 500. So halfway, this is 450. So it's 450. So therefore, half-life, the half-life is 450 years. Okay, 450 years. Okay, so that's how you can actually handle the graphical work when it comes to radioactivity. Okay, so now the last question is, they are saying californium 241 is also radioactive, and decays by losing an alpha particle. There's a half-life of 4 minutes. Suggests why it would be unsuitable for use in a smoke detector. Okay, so you can simply say this is a C8. So because it has a short half-life, making it to be replaced Okay, so it has a short half-life, making it to be replaced in the smoke detectors and making maintenance costly and impractical. So that is why it wouldn't be suitable for use in the smoke detector. So this is how you can just handle the questions concerning radioactivity on a graphical work. So make sure that you practice, and you'll be good to go. So thank you so much for watching, and I'll be able to see you in the next video. And ensure that you subscribe, like, and also share our videos. Thank you so much for watching. It's bye-bye.